Okay, so if we look back at this, you'll see that we have a possible point of inflection, right? So the possible point of inflection is what we're going to talk about. That's when the second derivative is 0, or when the second derivative is undefined. It's the same as a critical number with the first derivative, right? When it's 0 or undefined, when the second derivative is 0 or undefined. We talked about this. When the second derivative is positive, the graph is concave up. When the second derivative is negative, the graph is concave down. That's all that's saying, and we did this example. So I'm at a point where I want to do maybe one more example, which is right here. Now let's talk about the graph's concavity. When is it concave up and when is it concave down? Just another example so that you can try it out. Let's do it. So we have, let's see, the derivative is of course going to be needed, so we have to chain rule that. So e to the x, don't forget this rule, e to the x's derivative is always e to the x, so e to that is going to be e to that. We have that. But here's the deal, don't forget to chain rule that top part, this guy, right here. So this is what needs the chain rule. So what's the derivative of that? Well, I guess I would rewrite that as 1/2, negative 1/2 x squared. And that means that the derivative of that is going to be negative x, literally just negative x. And this is multiplication. So I would say that the first derivative is negative x e to the negative x squared over 2. So we found the first derivative. Of course, when we're talking about concave downward, concave upward, we need to find the second derivative. So we're going to need to take the derivative of the derivative. That's the second derivative, right? So f double prime of x is going to equal. Now we're working on this, but we have a product rule. So the derivative of the first is negative 1 times the second is e to the negative x squared over 2 times, plus the derivative of the second. We already did that because we already did, that was our original, the red writing was that. So we know that that's going to be this is the derivative of that second piece. And then we have to multiply that by the first, which is negative x. So it looks like our second derivative becomes negative e to the x squared over 2 minus x squared, plus x squared e to the negative x squared over 2. That is our second derivative. That is our y double prime if you prefer. Now we're at a point where we're going to find when this is 0 or when this is undefined. So finding out when that is 0 will be, let's see, well, we can factor out. We can pull out this part right here, right? So let's take out e to the x squared over 2, and we'll have negative 1 plus x squared, and we're trying to set this equal to 0. So I factored and set it equal to 0 in one step. That means I need to set each factor equal to 0. So that means the following. That means I have e to the x squared over 2 equals 0, and I have negative 1 plus x squared equals 0. So I have x squared equals 1, which gives us x equals plus or minus 1. That is a possible point of inflection, maybe. And it's going to go on my number line right now. Y double prime number line. And then I'm going to look at this. I'm going to say, okay, well, let's just talk about this for a moment. Is e to the x ever negative? No. E to the x, e to anything, right, is always going to be positive. So this is never going to hit 0. There's a horizontal asymptote there. It's never going to happen. So no possible points of inflection from this one. It doesn't really matter to us. So finally, we get to these numbers that we want to plug into our second derivative, which I guess is right here. And we want to plug those green numbers into that. Okay? So let's give that a shot. So we plug in, first of all, let's change those to blue just so we can have a little more clarity here. This is our second derivative. So if we plug in 0, we have e to the 0 times negative 1. E to the 0 is 1 times negative 1. That's going to be negative 1. This whole thing is going to be negative. Okay, now I have e to the, if I plug in 2, let's say I plug in 2 over here, okay? Well, when I do that, I have e to the 2 times 3, which in my opinion, positive times a positive, it's a positive. And when I plug in negative 2, I have e to the 2, which is positive, e to the 2, which is positive, times, and now I have a positive, because I have negative 2 squared, which is positive, so that's 4. So again, positive. So what I'm going to now say is I'm going to talk about the intervals of concavity. I'm going to look at that number line. That's really what I care about right now. But this number line in itself doesn't do anything. We need to explain it. The important thing is explaining what this number line means. So I'm going to quickly explain what this number line means. Look in that little box, okay? Okay, well, first I'm saying that it's the second derivative is negative from negative infinity to negative 1. So I'm going to say that it is concave up from that. And then when is it concave up again? Well, it's from 1 to infinity. So it's almost just like talking about increasing and decreasing, just we're analyzing the second derivative. And now it's concave down from negative 1 to positive 1. And this is y is, okay? Not y prime or y double prime. This is what's happening. Y is concave up and concave down from those to those. And that means if it's concave up to concave down, that means that there's a point of inflection when x equals 1 or x equals negative 1. So we found our point of inflections as well. So what you are going to do is to try this problem and have that done for tomorrow, and we'll see you then. You know, if you have other assignments, also make sure you get that done as well. Okay.